Good day, everyone. Thanks for joining this webinar. My name is Eric Su. I am Product Marketing Manager at Keysight Technology. I have been over 18 years experience in wireless test applications with Keysight Technology. From my past experience working with test engineers, 90% of the test engineers only use 10% of the signal generator features. They trust what they say on signal generator. In consumer wireless, military communications, or radar, you face an ongoing bandwidth crunch in the spectrum that is filled with interference. Test your device while signal simulation is critical. Signal generator provides precise, highly stable test signals for variety components and system test applications. Knowing the capability of the performance of your signal generator is the first step in making accurate and consistent measurements. In this webinar, we are going to discuss the best practice to optimize your signal generator. This presentation will cover 4 main topics. The first one, amplitude accuracy. Second, the wide bandwidth signal generation. The third, switching speed and the phase noise. Each topic including 2 to 3 best practice. Common signal generators are optimized for general purpose signal generation. Output performance of a signal generator is an optimized balance between measurement accuracy and speed. But nothing is immutable. Test signals can be high output power level or low output power level, wide bandwidth or narrow bandwidth, very clean or noisy, the CW continuous wave or modulated signal, and burst or non-burst signals. You need to know how to optimize your signal generator for specific test applications. This slide shows 3 major blocks for a vector signal generator: baseband generator, IQ modulator, and RF output section. Let's start with the amplitude accuracy in the RF section. RF signal generator tests component, receiver, transmitter, and systems. A wide output power range is required for a variety of applications. The output power range of a signal generator is determined by the step attenuator, which comprises different combinations of attenuator, and the automatic label control, the ALC, the circuit as shown in the right of the figure. The step attenuator provides close power attenuation, such as in 5 dB steps, to achieve the low power level. And the ALC circuit is used to provide power level adjustment within the attenuator whole range. Signal generator offer very accurate amplitude labels at their RF output port. In a common test setup, you are likely to use passive devices such as cables, filters, and switches, and active devices such as amplifier or mixer between your signal generator and device under test. These additional components cause insertion loads or gains to the test system. You need to consider these factors to ensure the accurate amplitude level at the input to your device under test. There are several ways to optimize amplitude accuracy while you use an external amplifier, attenuator, and other passive accessories with a signal generator. The common use method is to use vector network analyzer, VNA, to measure the gain or loss of the anti-signal path and enter the correlation value into the signal generator. So the first task, as shown on the slide, we need to move calibration plan to the test plan and ensure the accurate amplitude labels at the input to your device under test. The first best practice is use flatness correlation. User flatness correlation allows the digital adjustment of RF output amplitude to compensate the external losses in cables, switches, and other devices. By using power meter and sensor to calibrate the measurement system, A table of the power label correlation can automatically be created. When you add a component between a signal generator and the device under test, as shown in the figure, the red block, the calibration plane and test plane are not on the same plane. You must create a difference between the two planes. Please note, be sure to enter the sensor calibration filter into the power meter or signal generator prior to the calibration. Let's show you how to perform the calibration step by step. It's easier to use Keysight USB power sensor to calculate flatness. The signal generator works as a power meter and measures the power at the test plane. Figure above illustrates the flatness calibration setup by using a signal generator and USB power sensor. The first step, you need to configure the power meter and sensor. The USB power sensor can connect to Keysight S-series signal generator directly. Once the connection type and the USB sensor are selected, you can proceed the second step, zero the power sensor. The third step, open the user flatness table editor and enter the desired start and stop frequencies and the number of the frequency points. Or you can set individual frequency point as well. The fourth step is connect the USB sensor to the RF output. Set the output amplitude to 0 dBm and turn on the RF output. Then execute the calibration by push the Do Cal button. The fifth step, the amplitude correlation value will load automatically into the user flatness correlation array. Now the calibrated and test plane are at the same point. The correlation value can be saved in the signal generator memory. You can recall and apply the correlation values the next time you use the same test configuration. Please note, between the two frequency points, the correlation value is determined by interpolation, and you can use the legacy Keysight power meter sensor to connect Keysight signal generator through GPIP to perform the correlation. If you don't have the required Keysight power meter sensor, you can enter the correlation value manually. As mentioned in the beginning, the RF output power of a signal generator is constantly monitored and controlled by the LC circuit to ensure the output power does not drift over time or due to a temperature fluctuation. If the condition of the external components, such as amplifiers, degrades with time and temperature, the fixed flatness correlation cannot stop the amplitude drift caused by the external components. The figure shows an amplifier between the signal generator and the device under test. The amplifier's output power degrades with time. You have to extend the LC operation from inside the signal generator to the device under test input, the test plane. Best practice number 2, use external labeling. External labeling allows you to move the LC feedback signal close to the DUT so that it accounts for most of the power uncertainty inherent to the cabling and component in your test setup. As the RF power label at input of the power coupler changes, the external detector returns a compensating negative voltage. The LC circuits use this negative voltage to label the RF output power by rising or lowering the signal generator power. This ensures a constant power level at the input power coupler. Power loss is caused by the insertion loss at coupler. Be sure that your detector and the power coupler are specified for the power and the frequency range that you need. So the best setup procedures is similar to the flatness correlation. So you set the equipment, configure the carrier signal, select the external labeling, and determine the signal generator's amplifier ranges. The last step is to set the display the power value on the signal generator. In session 2, we are going to discuss wider bandwidth signal performance. When the signal bandwidth increases, it also changes the signal frequency response. The frequency response including the amplitude and phase error across the entire signal bandwidth. Let's explore what is the frequency response and how to calculate it in a baseband DSP. In the previous session, we used the flatness correlation to compensate the insertion loss of external accessories. However, the flatness correlation applies to a specific frequency point, amplitude compensation. At a different frequency point, a different offset value is applied for the amplitude flatness. When a signal is a modulated signal, the signal occupies a certain bandwidth. Only an offset value applied to the signal cannot create flatness effects for the entire signal bandwidth. The effects are not only amplitude flatness, but also phase flatness. So, how to calculate that? Best practice number 3. Use internal channel correlation. Most new vector signal generators support an internal calibration routine that calculates the correlation data for both the baseband and RF magnitude and phase error over the entire frequency and power label ranges. The correlation data, including the parameters of the correlation filter, applied to the baseband waveform in real time. The signal process is done in a digital signal processor. The figure above represents a baseband IQ generator. Before the dual deck, the digital to analog converter, the INQ, the DSP calculates the correlation filter and applies the filter to the baseband waveform in real time. So you see the red block. There are two correlation types, factory and user. The factory calibration optimizes the performance as the front panel output connected into a precision 50 ohm load. The user calibration can extend this performance to a new calibration reference plane and deliver the highest signal quality to the user device under test. This real-time channel correlation is important, especially for the wide bandwidth signal creation. Let's take a real case as an example. When you use a signal generator to output a modulate signal, the components inside the signal generator, such as mixers, filters, and amplifiers, result in different frequency responses at different frequency and output levels. The responses including both amplitude and phase response, and they degrade modulation quality. The figure above illustrates a demodulation analysis for a 16-4 modulation signals with a 30 MHz symbol rate, and the channel correlation is off. The error vector magnitude, EVM, is 1.89%. With the same signal and test setup, when we turn on the internal channel correlation, the EVM is down to 0.31%, and the IQ symbols are more concentrated on the constellation diagram. Best practice number 4, user channel correlation. Similar to the extending the measurement plane to the device under test input, the user channel correlation calibration extends the signal generator performance to a new calibration plane. That is the user device on the test input port. You can use a USB power sensor or signal analyzer to perform the calibration as shown in the figure. You need to specify the start and stop frequencies, configure analyzer, then execute the calibration. Once the frequency response measured, you can store the measured result to the signal generator and apply the correction filter to the baseband waveform to correct the amplitude and phase error caused by the external accessories. The correction procedures are similar to what we discussed about the flatness correlation procedures. Select the user calibration, configure instrument, set the frequency range, then execute the calibration. Please be noted, this calibration should be run when the ambient temperature has varied by at least plus minus 5 degrees Celsius from the ambient temperature at which the previous calibration was run. New vector signal generators, such as the Keysight VXG, the M9483B, or M9484B, allow users to embed it and de-embed it to correct the frequency response. You see from the figure, the block A and block B. You can add from the file. The file format can be S2P file, CSV, or the VSG support UFLAT, the file format. Or you can find measurement. So the instrument could be a power meter sensor, the signal analyzer, or the vector network analyzer, VNA. If you have multiple components with a different correlation file, they can be cascaded as shown in the bottom of the image. In session 3, we are going to discuss the fast switching applications, 3 types of switching speed of the signal generators, and how to speed up the switching speed. Today's manufacturers of wireless component devices and systems face a significant pressures to increase the throughput and lower the cost of the test. Improving the speed of the automated test equipment can be an important factor in reducing overall test time. In signal generator datasheet, there are 3 items related to speed: frequency switching, amplitude switching, and waveform switching. Each item is specified by signal mode and control method. The signal mode including the continuous wave and the digital modulation mode. Control method including the skip command, the remote control, and the list and swap method. When the signal generator is set to a new frequency, the frequency synthesizer will change its output to a desired frequency. The output amplifier will then adjust the output level so that the output power stays the same at the new frequencies. Essentially, the frequency switch requires to change both frequency synthesizer and the output amplifier, which is why frequency switch is often slower than the amplitude switch. For digital waveforms, the IQ waveform data must be computed and downloaded into the playback memory. The sampling rate and the digital to analog converter values must be computed and stored with the file for the accurate playback. There are various ways to control the signal generator output in automatic test systems. It's straightforward to send commands to a signal generator for setting frequency, amplitude, and waveform. This is useful when the frequency, amplitude, and waveform states are not initial known. Due to the command sending, phasing, and processing, there is an overhead time when using the skip command before the switching can begin. If the frequency, amplitude, and waveform combination are known in advance, then using the step or list swap, which can switch multiple parameters simultaneously, is significantly faster. The step swap offers the linear or log progressive from one select frequency and amplitude setting to the next, paused at the linear or log space points along the swap base. This swap enables you to enter the frequency amplitude on equal interval in a nonlinear ascending, descending, or random order. In addition to amplitude and frequency, you can also switch a baseband IQ waveform at the same time. You need to provide the frequency amplitude labels, waveforms, and dwell time at each point. For fastest switching speed, use this swap. Before you enable the swap, you need to configure the swap trigger and point trigger. The trigger setup can be free-run trigger key. A trigger key is a front panel button, or bus, a trigger on remote command, or external trigger or internal signal. Best practice number 6, digital baseband tuning. For most wireless device production tests, the speed of the test process is often limited by the device itself. The test response time of the device is typically measured in milliseconds. Traditional signal generator analog frequency and amplitude tuning speed are sufficient to support a device-stable production test. The ultimate speed challenge occurs at the RF component level of the wireless food chain. For example, the RF power amplifier, transceivers, front-end module, system-in-package, system-on-chip require fast test speed in the production line. Digital baseband tuning techniques offer the ability to digitally shift both frequency and amplitude labels of the signal within the vector signal generator available modulation bandwidth without needing to retune the synthesizer. Digital baseband tuning introduces a new vector signal generator architecture that is dramatically faster than the traditional RF tuning techniques. So the speed improvement compared to the RF tuning for programming and command is up to the 40 times. For this mode, it can be up to the 22 times. But the limitation for these techniques, the frequency range only the maximum modulation bandwidth of the signal generators, and also the amplitude range can only up to the 20 dB. Next, we will discuss the major specs of the signal generator, phase noise, how to optimize the signal generator phase noise profile. The phase noise performance of a signal generator is a key factor in obtaining accurate measurement. It can be a limiting factor for many applications, such as IC component testing, wireless device testing, and radar testing. These applications require signal generator with ultra-low phase noise at different frequency offsets. You need to understand where you care most first. Most vector signal generators are phase-locked loop-based architecture, which includes the reference oscillator, synthesizer, voltage control or EEG oscillator, and output section. Each section has a different effects on the phase noise characteristics as shown in the figure. For offset below 1 kHz, the noise is dominated by the performance of the reference oscillator, which is multiplied up to the carrier frequency. From offset 1 kHz to roughly 100 kHz, the synthesizers influence most. The VCO and EEG oscillator is from 100K to 2 MHz. And the output amplifier is offset about 2 MHz for the broadband noise. Best practice number 7, adjust the reference oscillator bandwidth. At a frequency offset below approximately 1 kHz, the stability and phase noise are determined by the internal or external frequency reference. It's straightforward to have a stable and extremely low phase noise reference oscillator that improves the carrier phase noise in offset frequency range below 1 kHz. The Keysight VSU signal generator provides an option to input a closing phase noise. The reference oscillator bandwidth, sometimes referred as a loop bandwidth, in a signal generator, is adjustable in fixed steps, shown on the upper figure, different colored curves with selected oscillator bandwidths for either an internal or external 10 MHz frequency reference. Keysight MXG allows you to use an external reference and select the either narrow bandwidth, the red curve, or the wider bandwidth mode, the blue curve. You can select different optimized phase noise curve for your applications. Best practice number 8, phase lock loop bandwidth. In the synthesizer section, you can set the phase lock loop bandwidth to optimize phase noise above or below 150 kHz on Keysight PSG signal generators, as shown in the figure. The light blue curve is optimized below 150 kHz frequency offset, and the yellow curve is optimized about 150 kHz. Evaluate your application to choose the appropriate phase noise setting for the wider offset frequencies. Best practice number 9, real-time phase noise impairments. Optimizing phase noise performance is not always necessary or even desirable. Some applications and tests require a specific amount of the phase noise for accurate signal substitution and tolerance testing of the phase noise. The Keysight RF signal generator N5182B or N5172B allows users to adjust the phase noise impairments on the synthesizer session. This feature lets you to degrade the phase noise performance of the signal generator by controlling 2 frequency points and amplitude value, as shown in the figure. This customized phase noise is produced by internal algorithm of the signal generator, operating on a real-time baseband ASIC and processor oscillator. This allows you to simulate a more realistic signal and is helpful to evaluate and troubleshooting your device under test. The signal generator degrades the phase noise by moving middle frequency characteristic and changing the amplitudes using the following setting: the start frequency F1 and stop frequency F2. The amplitude, the L mid. The close-in and far-away phase noise characteristics are -22 dB per decade. To summarize today's presentation, signal generator provides precise, high stable test signal for a variety of the component and system test applications. Different applications have different performance requirements. Keysight signal generator offers flexibility and diverse capability to optimize performance and measure speed. The best solution will come from your experience, insight, creativity, combined with signal generator and measurement software that enable you to generate the signal required to effectively to test your device under test. To find more information of signal generator, visit Keysight signal generator website, www.keysight.com/findsg. Here are related resources, including reference document, white papers, application note, Keysight RF and microwave industry insight blogs, social media like Facebook, and LinkedIn for RF and microwave test. Thanks for watching today's webinar. I hope you learn these tips and apply them to your test applications.
Thank you, Eric. Before we begin our question and answer session, I'd like to call your attention to some survey questions we'd like you to answer. If that window does not show on your console, please click the icon in the widget bar located at the bottom of your screen. Here are the survey questions. Number 1, how would you rate the overall technical content of this webinar? Number 2, after viewing this webinar, do you have a need for any of the solutions listed? Number 3, if you have a need, what is your time frame? Number 4, what are your key business challenges? And finally, we have provided space for you to let us know if you would like a follow-on meeting or visit with our local sales and support experts. And finally, if you have any additional comments for future topics. Now it's time for our question and answer session. If you would like to ask a question, please click on the Q&A icon in the widget icon at the bottom of your console. We will try to answer these questions during the webinar, but if a fuller answer is needed, or if we run out of time, we will answer it later via email. Please note that we do capture all of your questions. So let's get started, Eric. Here's our first question. Can we use legacy Keysight power meters and power sensors to create a user flatness correction array? For example, can we use an N4419A power meter with an E4413A power sensor or a non-Keysight power meter?
Okay. Yes, you can use either GPIB or LAN cable or USB interface to configure your Keysight power meter sensor. Yeah, if you don't have the required Keysight power meter sensor, or you don't have or your meter doesn't have a LAN cable, GPIB, or USB interface, you can enter correlation value manually. But I would say the USB power sensor is the most cost-effective choice, as a Keysight S-series signal generator can work as a power sensor. Yep.
Thank you, Eric. Here's a second question. The channel phase and amplitude corrections are important in order to make an accurate measurement. Why does Keysight just set it as default?
Oh, okay. So actually the default setting of the internal channel correlation is off. That is because the general purpose signal generator are optimized for performance, accuracy, measurement speed, also cost of a test. And most of the test scenario are narrow bandwidth, and they just need just enough performance. And some customers, they need the high speed measurement, high measurement speed. So when the correlation feature is on and the frequency changed or amplitude changed, the signal generator firmware will calculate the channel correlation filter. This process requires additional time. So the amount of the test time and the switching time depends on the type of the frequency switch. So the channel correlation has few impacts on the measurement results of the narrow bandwidth of the signal generator. So usually it's not necessary it's not necessary to turn the channel correlation on because it increases the test time. So I also did some experiment for Keysight signal generator. Yeah, for example, I did an example like a 64 crane modulation scheme at a different symbol rate. So that means the different bandwidth. I did a bandwidth symbol rate like 10 megahertz, 30 megahertz, and 100 megahertz. So the result for the modulation quality, like EVM performance, the difference between the internal channel correlation on and off is around, for 10 megahertz symbol rate is around 0.1 to 0.2% for the EVM. very few. And for the 30 megahertz symbol rate, it's around 1% only. And if you the bandwidth up to the 100 megahertz symbol rate, actually the analyzer cannot demodulate the signals. So as the bandwidth increased, the frequency response will impair the modulation quality very seriously. So if we just want to test the signal very quickly and for narrow bandwidth, so you don't have to turn on the internal channel correction. But if the signal bandwidth is wide, like more than 30 megahertz bandwidth, like 100 megahertz bandwidth, like 5G, you have to turn on the internal channel correlation. Yeah, that's the answer.
Okay, thank you, Eric. Okay, we have one more question. You mentioned that the digital baseband tuning technique is used to improve switching speed. It's about 10 to 20 times switching speed improvement compared with RF tuning. What are the limitations of this technique?
The baseband tuning technique is a new technique to improve the speed. And the first limitation is bandwidth, of course, because we're doing that in the baseband generator. So the bandwidth of the signal generator will be the key limitation. So the switching frequency cannot over the, for example, the Keysight MXG cannot over the 160 megahertz bandwidth. Yeah. And the second limitation is amplitude dynamical range. We can only allow user to set like a 20 dB. If you set the 0 dBm on signal generator, so the maximum the range is only minus 0 dB to minus 20 dBm. So that's only two limitations. But either frequency and amplitude switching are over the loss limitation, like a frequency, like the amplitude range. You still can perform the analog RF tuning to the next range. I would say the most of the test application doesn't need such kind of the ultimate test tuning speeds. So Keysight implements this feature in PSI modular signal generator only. Yeah, you can contact Keysight's sales representative for more information. Yep.
Okay, thank you, Eric. It looks like we'll have time for one more question. With respect to phase noise profile adjustment, Keysight has several ways to modify the phase noise, but this does not apply to all Keysight signal generators. For example, the real-time phase noise impairment is available only on the MXG and the EXG. Can you comment on that, please?
Yeah, sure. As I mentioned in the beginning of this presentation, so the hardware performance will depend on the hardware structure and your applications. For example, for the microwave frequency, like the testing application like a radar, they require a better close-in phase noise. So Keysight, like a microwave signal generator, like a PSG, we offer a multiple option to address this reference section to improve your close-in phase noise. Another case is like a RF frequency, like a below 6 gigahertz. The application like a commercial communications. The engineer, they only care about the synthesizer or oscillator and output section, like for example the OFDM signals. So that would be in synthesizer section, the frequency offset. So the new Keysight S-Series VSG, we offer several options to optimize the phase noise. Even we can adjust the phase noise impairment, as I mentioned in these presentations. That will be for accurate signal substitution or tolerance testing for the phase noise. And I think in overall, that will be it's a trade-off for the cost, for the speed, switching speed optimization, for the far out or closing the offset phase noise. So I would say the applications drive the signal generator hardware performance. Yeah. That's my comment on that.
Okay, thank you, Eric. Thank you for this great information. So that's all the time we have for Q&A today. We will respond to your other questions via email. So thank you very much. This concludes today's webinar. As a reminder, you'll receive an email when the recording becomes available. Download the slides now in the Resources widget. Thank you for attending today's webinar brought to you by Keysight Technologies. Please join us next month for the continuation of our Engineering Education webinar series and enjoy your day. Thank you.